Good luck on it.
All right, you guys ready? All right. So I have my bowling ball, as you can see. I have my bowling ball, as you can see. And now, if the bowling ball rolls a little bit, it's because the floor may not be perfectly level. But what's that? I don't know. It just isn't.
Maybe because of like
All right. So can you see the ball?
like this drain here.
All right. What do you notice about the ball?
It's at forces are balanced.
So I think Danny's right. Is it moving?
No.
Is it an object at rest?
Yes.
What is the natural tendency of an object at rest? To stay at rest.
Because the
As long as what?
forces are balanced.
Forces are balanced. That's correct. All right. So if the forces are balanced, the acceleration is 0. It says it on the board, and it doesn't go anywhere. Cool. Everybody feel okay about that? All right. So if you don't have that written down, I want you to write that down right now. The natural tendency of an object at rest is to stay at rest as long as the forces are balanced. In middle school, your teacher would have said, unless acted on by an outside force.
Yeah.
I don't really know what that means, because like the floor is pushing on the ball, it's outside of the ball. I don't know what outside, like outside of what? Do you see my question?
External force
Right, but external to what?
to the normal force and the ball.
Can you just say unless
Because the
outside
floor,
by
because the floor would be the normal
But
force.
if I push down on the ball, it's still an object at rest. I just push down more, the floor pushes up more.
Yeah, well,
Forces are still balanced.
That's what I'm saying. That it remains at rest
That's
unless
what
it's
it's
acted on by
put,
unbalanced force.
Okay. So I like what Brendan says. He says, look, it's going to stay at rest as long or until it's acted on by an unbalanced force. That seems reasonable. Are you ready? I'm going to roll this at you.
That's how I do
Are you ready?
No.
Are you sure?
Yeah.
During I did this during third hour. I rolled into a girl, and I am under the impression that if a bowling ball is coming at you, you're going to put your foot up to stop it.
Maybe.
She let it like roll right up her foot. She's like, oh, that hurt my toes.
Who was it, Bella? It was Bella.
It was counter tubs.
Are you ready? Here it comes. Now, tell me, until it hits Annabelle, did you?
Yeah, I think the floor is on level. It
Well,
looked like it was going faster.
Oops.
let's watch. Okay? Tell me what you notice about the ball.
Okay, now we can
What do we notice?
It doesn't stop.
Okay? So, did you notice that the speed was constant? And did it go nice and straight? It does. I mean, and this is actually contrary to what happens like if you guys go bowling and you roll it and you notice the ball is drifting left a little bit. You like kind of lean right, hoping this is going to somehow have some psychic, right? So what do we know about the natural tendency for an object in motion? Stay in motion. What kind though? Straight line at a constant speed. That's right. You guys got this?
So then why does the bowling ball turn?
Well, because you didn't roll it straight.
But
Then
that
it's gonna
might be
release
true.
the ball.
Sometimes I do have two in legs, so it's actually straight. Why would you do that?
But
I mean-
again, you can't get away from this. The natural tendency of an object in motion is to stay in motion in a straight line. Just because you think you rolled it straight doesn't necessarily mean you actually rolled it straight. Not personal. So if you don't have this down, make sure you get it down right now. The natural tendency of an object in motion is to stay in motion in a straight line at a constant speed. But this is also true as long as the forces are balanced. And this is actually a fine demonstration because you watch the ball and it doesn't slow down or turn on its own.
Oh, did you want me to leave it going?
No, I want you to send it back.
Take it back.
Okay? So,
We should let him hit the wall and one straight.
We already like broke the
so today what you guys are going to do, okay, is you're going to explore these relationships for your own. Because if I want to get this going, I need to apply some sort of unbalanced force to it. Okay? I need to apply some sort of unbalanced force to it. So I'm going to use my little meter stick here. You guys are going to either use a little ruler or you're going to use a whiteboard marker or whatever, okay? But what happens if, let's say I'm going to like just get this going a little bit. What happens if I push it in the direction of motion? What do you notice happens to the speed?
Accelerate.
Does it look like it speeds up?
Yeah.
It does, right? And what happens if it's coming this way and now I apply a force this way? Now what happens to it?
Forces are imbalanced.
So did we see a change in the velocity?
Yeah.
We did, right? Is that a result of an unbalanced force?
Yeah.
It does appear that way, right? So that's what you guys are going to do today, and you're going to explore 5 different instances of this. Okay? You guys are going to explore 5 different instances of this.
What balls? That definitely.
At the station, you're going to find little pool balls, little cue balls.
Same team.
Okay?
Oh, we should play pool.
We could make one out of
We should have a day and
That's actually good
and
physics.
we can play pool.
Listen, all
And
this
then
stuff
we
is
can like
good
study like
physics.
the angles of like the ball.
Pool,
In that case, we should
darts,
play tennis.
bowling.
It's
It's all physics, man.
So why don't we do it?
It's all
in the
physics.
pool. Yeah, let's go to the.
These are leisure activities. Leisure
But they're
activities.
No,
physics.
there's physics activity.
Let's play pool in the pool, so it's like instead of the pocket, you
It's
gotta
got a mind of its own.
All right, number 1.
Dangerous.
Okay?
You're constructing.
There are 5 different. I want you to write them down. Are you ready?
Yes.
5 different. Number 1. You are going to apply the force in the same direction as the velocity. Okay? You're going to apply your force in the same direction as the velocity. So, in number 1,
Oh.
the ball is moving to the right, and the force you're applying is to the right. Constant force. Okay?
Yeah.
And we saw that demonstrated that. That one I think you'll understand pretty easily.
Wait,
Number, what?
What did we write that?
Apply the force in the same direction.
So you're applying the force in the same direction as the velocity.
Ooh, we should draw that. I
Is
really.
that a beyond topic?
It is.
Number 2.
In number
We're gonna go
2,
planetarium.
you have the velocity going the other direction, but you're still applying the force the same way. So this time you're applying the force constantly opposite the direction of motion.
Well, wait, if you're applying it constantly, but it's in the same direction, it's gonna accelerate though? Isn't that what you just, okay, I just was confused though.
No, I mean, that is exactly correct. So what Sophia said was, wait, if you are applying the force in the same direction that it's already moving, your acceleration and velocity are going to be in the same direction, you should be speeding up. I think you're going to find that that's true. Okay? Now, the third one is actually a little bit more challenging. You're not going to apply a constant force, you're going to apply an instantaneous force. Okay? So what Annabelle's going to do is she's going to roll the ball at me.
It balanced.
She's going to roll the ball at me.
Okay.
And I'm going to give it a instantaneous kick perpendicular to the direction of motion. So it's coming at me, and I'm going to give it a boop, just a little kick like that.
Ooh, that really was.
That was probably
Is that how it's supposed to work?
Anticlimactic.
Did you do it right? Because it kind of went.
I kind of missed it, but
Kick the
we'll see what
Well, I
happens.
guess you'll try it.
Go ahead. Here it comes, and I'm going to go boop.
Did that hurt?
Nope.
Those are so strong.
Really not.
Did you see what happened there? Now, you're going to do this at your station so that it makes some sense to you. So in this one,
Mr. Paddock, can we roll it down the hallway and see if it keeps going?
It will.
Watch out, there's a bowling ball coming at
Thank you,
you.
pass it to Miss Aspen.
And then
Hey,
Get across.
what?
That was good.
Get it!
I
Now I
said
know what
Jacob's head will stop it.
Oh
Now,
my God.
this next one, okay, this next one is like this but different. See, what's going to happen in this one is the ball is going to be moving, again, perpendicular, so it's moving this direction, and you're going to push in this direction, all right? But you're going to use a constant force, okay? You're going to use a constant force. So Annabelle's going to roll the ball at me again. And this time, when it gets to me, I'm going to start pushing it toward the back of the room. Alright, now I have a sense that it's going to start moving that direction at least a little bit, and I have to keep applying the same force. You guys with me? Go ahead. So it's coming toward me, and it's going to get here, and I'm going to start applying a force like this. Alright? Okay.
So you're applying force like that.
No, I'm applying a force directly toward the back of the room. Okay? Brendan asked a great question. He said, are you applying a force at an angle? No. Like, I'm literally going to start pushing this way, just to the back of the room. Now, the ball is still moving to the right, because once you're an object in motion, your natural tendency is to stay in motion. If I wanted it to slow down, I'd have to push it back toward Annabelle. Right? So go ahead. So I'm going to push it this way. Now, I'm going to keep pushing it. I just don't want to, bend over and crawl on the ground. You guys got me? So, this one, you're going to apply a constant force, okay, that's perpendicular to the original direction of motion. Okay? You're applying a constant force that's perpendicular to the original direction of motion. So set up on here, I'm applying a force toward the back of the room. Okay?
So what are we recording? Like what kind of data?
What kind of rabbit? He looks very engrossed. I was like, what is she doing now? Okay, now, this last one is the only one that's actually kind of hard.
Says you.
Okay? This one is actually a little challenging because what you're going to have to do.
I just drew the same as
What happened? Oh, what happened?
They're having a fight right now.
Mr. Pettit,
What?
what's the letter on the side?
F?
And the other one.
V?
Alright, thank you.
Escalating your voice is disgusting.
Now,
We do not.
this one is really challenging to both understand and do, but it is the one that's important. Okay? I'll take the ball. What we're going to do this time is it's going to start off like the last one. Okay? It's going to start off like the last one. Isn't that cool? Like once I get it in the way I want it to go, I can just stop pushing it. It just keeps going that way. Very much like curling, actually. When you curl, like they spin the thing, and it rubs against the. So if they spin it this way, it rubs against the ice, and it causes it to curve.
Like bowling.
Right? Kind of like bowling. So bowling has is another feature that I don't want to talk about right now. We can talk about it later. Maybe during our bowling field trip. Just kidding.
Say that and then take it.
Whoa, that's like illegal.
We
You
will
can't
bring
just
it
say
like
that.
Mr. Carter paid for it. We'll bring it $5. No.
Yeah, I agree.
Go after.
When are we going
Hey,
to remember when I asked you why helium defies the laws of gravity?
It doesn't.
Remember when I asked you why bounces
No, I'm
one way
saying
and down
it's
and
all
one way up?
Yeah.
So like a helium balloon, like gravity just doesn't work.
No, it does.
It doesn't.
It does.
Why does it go up?
Because there's a force up greater than its weight.
What's the force up?
The air around it.
What? So why does a balloon
No, I can call now.
not have the same force
Because it's
up?
heavier than a balloon with helium in it.
I just thought helium is a myth and doesn't actually exist
What?
in Canada.
That makes 0 sense.
Anyway, watch closely. Alright, this time, what I'm going to do is, when it gets here, I'm going to push it perpendicular to the direction of motion. But then, it's going to change the way it's going, and then I'm going to change the direction I'm pushing, where I'm always going to push perpendicular to the direction of motion at that moment. Okay? So go ahead. So it's coming in here. I'm going to push it perpendicular, and then perpendicular, and then perpendicular. You're always going to push it perpendicular to the direction of motion. Watch what it looks like. Okay? Okay? Let me show you what it looks like. We're flying. We're flying.
So we actually are going on a roll.
I hope so.
I mean, it's on record now, so we can use that against you.
Maybe to the planetarium at least. Oh yeah, we can do it. You know what? Somebody should bring a pool table and we can play pool.
Can you play Epic?
I think that's the best.
Gentlemen, ladies,
Yes.
reset please. Here's what this one's going to look like. So the ball is moving in this direction. So if I look at the ball over time, okay, and then now I'm going to apply a force right there. So the ball is moving this direction, I'm going to apply a force there. So at this moment, the velocity was down, and I'm going to push to the right. But that's going to change the direction of motion of the ball, right? A moment later, because it was moving down and it got pushed to the right, the ball is going to be here, and its new velocity is this way. Which means you're going to push it that way. You're always going to push perpendicular to the instantaneous direction of motion.
I'm very confused by that.
No problem. That means you're ready to learn. Now, you're going to do all these, and how are you going to represent them in your notebooks? Great question, Don.
Motion maps.
I swear to God, those 6
Now,
times.
We're doing a motion map together?
because I know how much you love motion.